Hi and welcome to the second part of drivers and devices. In the previous video we've seen how drivers and devices interact. A driver represents the code for a driver and generate behavior, and device represents communication endpoint. Devices typically have names and we open handles to devices. We've seen that one driver can maintain and manage multiple devices which are stored as a linked list. A device can represent a physical device or a virtual device. In this part, I want to show you how to access devices by opening handles to them. In order to open a handle to a device, we need to use an abstraction called a file object. A file object is a type of kernel object that can hold a reference or point to a device object. So this device object again could be physical or virtual, doesn't really matter, but it represents some kind of device we can communicate with. So there's no open device kind of function, there's a create file object function, which in fact accepts as its first parameter not really a file name but actually a symbolic link, which could point to a file name as a particular case. We've seen that C:, D:, these kinds of things are actually symbolic links, they're not that fundamental and they point to device objects. And so the file name, as the documentation calls it, is actually a symbolic link. What happens if we have no symbolic link? What can we do in that case? So I'll show one or two options to solve this kind of conundrum. So let's start with a simple example. Let's say I would like to open a handle to the Process Explorer device. We know that Process Explorer has a driver, and we know that this driver has a symbolic link called ProcEXP152, which is pointing to the actual device object ProcEXP152. The global two question marks directory in the Windows Object Manager namespace, we can see with the WinObj tool, points to all these symbolic links. All these are valid values to the create file function. So let's start with ProcEXP152, try to open a handle to that. So here goes, we need to have a handle being obtained using the function create file. Create file requires several parameters. The first one is the file name, but it's not really a file name but a symbolic link. In order to indicate this is in fact a symbolic link, we have to prefix that with two backslashes, a dot and a backslash, and then provide the name of the symbolic link, in this case ProcEXP152. Why do we need to provide this prefix? The reason is that without this prefix, the IO Manager parser assumes this is a file name in the current directory with no extension. This is because this is probably the most common case, but still we need to tell the IO Manager, the parser there, that we're actually looking at a symbolic link. So we have two backslash, a dot and a backslash. So we have to duplicate any backslash here because of the way backslashes need to be escaped in C. If you would like to remove that problem, we can use one of the features in C++ 14, which allows us to prevent escaping of backslashes. So this is essentially the same thing. Then we need to provide the access. So I don't want to be very specific here. I want to have a generic read and generic write access. I'd like to ask the driver to do something for me. I want to give it some information, get some information back. And then there's a share mode, which has no meaning for devices, only to actual files in a file system. Then we have some security attributes, which also don't mean anything because we're trying to open a handle to an existing object and not trying to create a new one. So the security descriptor is not really up to us. Then we have a creation disposition parameter, which should be open existing. That's the only value that makes sense for devices. We can only open handles to existing devices. Then we have a bunch of flags, not important for our discussion. Another parameter called a template file, which is again not important for our discussion. So if this thing fails, we get back invalid handle value. Then we know something went wrong, we can just display the error. Or let's just do the opposite. If we don't get invalid handle value, then we can talk to our driver, to the driver using the device handle that we have in hand. So we can say, okay, great. We have a handle here. We can even display its value if we care. It doesn't really matter the actual value, but let's display it just for fun. And then we might want to talk to the driver in some way. In this case, I'm just going to close the handle here. So let's see if that works. I'm going to put a breakpoint here and press F5 to build and run this application. So I'm trying to open a handle to this device and notice I failed. We can see the handle to device is -1, which means we failed. So let's see why. We can go to the watch window and use the pseudo variable @err to see the actual value of the error. You can see it's 5. You can probably guess what that is. We can add the "HR" to get textual description. You can see it is error access denied. So we don't have enough access, and the reason is that the Process Explorer driver protects its device so that only administrators can open a handle successfully to that device. So let's try it by running Visual Studio again with admin privileges. So restarting Visual Studio here with admin privileges. Let's try it again. I'm just going to press F5 without making any special changes. Here goes. Now you'll notice it works. If I look at the handles here, I see a proper handle with a value A0. Let's look at what that is, well, in Process Explorer. So let's look at our client application. It's called Dev Access. That's the name of this little application. And let me look at the handles here. And looking at the handles, you'll find that the value that we're looking for, this is a value for a file object. Let's sort by handles or by whatever means that we see fit. We can see here that the actual handle is here and it is pointing to device ProKeyXP152. So it's actually pointing to the target device object. So this is exactly the target here, device ProKeyXP152. So the file object points to the device object directly, sort of walking through the symbolic link. So symbolic link is no longer important or in the way. The handle points directly to this device object. The next thing to do, of course, in this particular case is try to do something useful with the handle. But of course, in this case, we need to know how to talk to the Process Explorer driver. For that, we need some kind of documentation, which doesn't exist, or doing some reverse engineering, which I'm not going to do here right now. And then once we're done, we can close the handle. Let's try something else. We know there's this device called the beep. And the beep device is there to play sounds. So maybe I want to open a handle to this device. However, if we look at the global 2 question marks where we find all the various symbolic links, you won't find anything that's pointing to beep. In fact, we can verify by doing a system-wide search for anything that looks like beep. And you can see there's a driver called beep in the driver directory that we've seen in the previous video. And we have a device called beep, but there is no symbolic link. What can we do to gain access to that particular device anyway? So there are a few options we can use. The first option is actually a trick which is not, I think, officially documented, which is to use something here called global root, which points to the root of the Object Manager namespace and then use device beep to actually reach the device. This is a little trick that should work. It works in many cases. Let's try this. So I'm running this with the debugger again. Let's do F10 and we do get a valid handle. Going back to our process, of course it's a new process by now, but let's find it again. Here's Dev Access. You'll notice that we have a handle here that's pointing to device beep exactly where we wanted to be. So it does work. That's one way of gaining access to a device without going through a symbolic link, because there is no symbolic link in this case. By the way, this global root, if we look at WinOBJ, global root does exist here. If we do a little filtering here, here's global root, which is pointing to the root directory. There's nothing here, but in fact, it is pointing to the root directory. And then we go to device and then beep. So you can select any device here to try to talk to it. Of course, it's not enough to be able to open a handle. You also need to know how to talk to the device to get the desired effect, whatever you'd like to happen here. So for example, with the beep device, I might want to play a sound, for example. And for that, I need to know what to call. Should I be calling read file, write file, or device control? Again, I require some documentation or doing some reverse engineering. Fortunately, by the way, for the beep device, there is documentation that is provided by Microsoft in a header that has this name NTDD beep, which is a header that can be used in user mode and in kernel mode. And with that, in fact, we can play a sound. If we go to this header, let me open that header for a moment, you notice that we have some stuff here we can use, such as the device name in this way, with ASCII and Unicode strings. And then there's a control code here we can use in order to talk to the device and make it play a sound. And this control code has this constant called ioctl beep set, which is made up of several parameters here that are provided to a macro called control code. I won't be covering control code in this video, but we can just grab this value as is. So what should we give to that control code when we call device IOControl? There are two buffers we can provide, known as input and output buffers. In this particular case, only input buffer is required, and this is what we need to provide. We just need to provide the frequency and duration for the sound. So let's give it a shot. Let's go ahead and create one of these data structures here. Let's call that note. Let's create some kind of note. Let's say a frequency of 100 and say duration of 2000, like 2 seconds. The duration is in milliseconds and the frequency is in hertz. So once we have that, we can go ahead and call device IOControl, which requires the handle to the device, the control code, which we now have, that's going to be beep set, and then our input buffer. Our input buffer is the buffer we just filled out, this note, a little note structure, the size of note. There is no output buffer, and so there's no size for the output buffer. There's a value we get back as to number of bytes which were actually used by device IOControl, or to be more precise, in the case of device IOControl, it's the number of bytes that were placed in the output buffer. Although we don't have an output buffer and we don't care about any of that, it's still something we have to provide. Putting null there will cause an access violation exception in user mode, and then we're essentially done. And you might be thinking, what's the advantage here compared to calling the beep API, for instance, which also uses exactly the same strategy to play a sound. So the only difference in this case, beside being more interesting doing things manually in this way, is that this is going to play the sound asynchronously. So we can continue doing other stuff while the sound is playing. The beep API always plays the sounds synchronously, so it waits internally until the sound is done. So first, let's see if that actually works. So here I'm opening the handle to the device just like before. We have the handle value. I'm setting up the frequency and the duration and using device IOControl. And there's a sound. I'm not sure this is being captured. I hope that it is. There's a sound. Feel free to try it yourself. Then we can close the handle and we're done. Now I mentioned there are other ways to get a handle to a device if it has no symbolic link. That was one way. There's another way that uses a native API. So I want to show that as well. And this native API is the function that we need to use called, well, NTOpenFile. That's the function. And so NTOpenFile is a native API and not normally provided by the normal Windows headers, but it is actually documented in the Windows driver kit, and in fact even provided by a header Microsoft doesn't like people using, but still they provide it. It's called winternal.h, and winternal.h has some definitions related to the native API. If I press F12 to open this file, you'll find some definitions such as anti-status, things like Unicode string, which is a structure used to represent strings within the native API and the kernel as well, and some of the functions that are available to native APIs. One of them is NTOpenFile, so it is here and we can now actually use it. So let me quickly show you how to use this function to gain the same kind of access, but do that in a more direct way, because NTOpenFile, being a native API, can accept the full path of any device object anywhere in the Object Manager namespace, and it is not limited to anything that is accessible using symbolic links. So we need to get some status here. That's going to be our result. This is a way to see whether we have succeeded or not. NTOpenFile requires other kinds of parameters which perhaps we're not very accustomed to when we're working with user mode. The result is going to be into this handle, this H device, so I'm going to pass the address to that. Then we have the access mask, which in this case, just like before, we can use generic write. In fact, read is not really necessary here because we can't read from a beep device, we can only write to it. So that's actually good enough, just like we could have done the same thing in the previous example. And then we have something called object attributes, which is where the name of the device is going to be stored. So we have object attributes. Let's create this structure, which is very common in native APIs and kernel APIs as well. So let's call that dev attributes. And also we need to have the name as a Unicode string, which is going to be stored inside the object attribute structure. So let's call that dev name. And in order to initialize that, we can initialize that using the function RTL init Unicode string. Dev name here and the source string, which is exactly the string that we need that points to the device object, which is going to be device beep, just starting from the root. Or we can take advantage of the fact that NTDD beep provides that string already for us. We can grab it. This is the one here. I can just take this thing here to make it perhaps more generic in nature, maybe if that something changes sometime in the future, unlikely, but still we can do that as well, just to show another option. So we have this initialization of this Unicode string with this non-terminated string. And then to initialize the object attributes, there's a macro that we typically use called initialize object attributes. So let's try to call that if I don't make silly mistakes. So initialize object attributes. We need to provide the object attributes and then a bunch of parameters. The most important one is the name. The other parameters for now are not important enough to discuss. Once we have that, we can finally move forward with NT-OpenFile, and the next parameter is the object attributes. And then we have something called the IO status block. So this is actually a result. I'm going to create this structure called IO status block. We don't actually care about the result technically within this structure, but we have to provide something there. And there are some flags we can specify and some share access, which are not important for this particular case. So now if this works, we get a success status here. So it means status is status success. That's one way of specifying that. At least I can try. So if we get status success, which is just 0, it means everything works as planned. So unfortunately, it seems that status success might not be properly defined. Let's just use 0 here. That's going to be good enough. And once we have that, the rest is the same. We're calling device control to play the sound. So let's see if this works as I hope it would. So notice that we can't really properly link the application. That's because using two native APIs here coming from NTDLL. And since NTDLL, the import library is not by default set in new Visual Studio project, we have to edit ourselves. And the simplest way of doing that is to add that in the source code, like so. Let's add that ntdll.lib. So this import library is provided by Microsoft, but not added by default because normally we don't need it. We just use public document APIs which are not coming from NTDLL. And now it links successfully. So let's try it now. Let's run. We have our device name here, which has some junk, but after we initialize that, it's properly initialized to the string that we want, device beep. Then we initialize the object attributes and finally calling NT-OpenFile. And let's see what happens here. We need to get a handle here in H device and it works. We get the handle A4. Again, we can go back here and look for our application dev access, and A4 is the handle value pointing to device beep. So it works in exactly the same way, but using the direct path to where the device object is without having to go through any kind of symbolic link. This is one of the powers of NT-OpenFile. And again, the name file here just means file object. From that point on, we can continue normally and playing sounds and things like that. So this shows you how to open handles to devices. There's actually a third way of getting to a device that doesn't have a symbolic link, but I'll leave that to you to explore on your own. But beyond that, feel free to take a look at the various tools like the kernel debugger and WinObj, and see what's going on when you create these kinds of objects and handles and how this all works internally.